Good morning, students. Today is the 29th session and we are going ahead with the topic crystal field theory. In crystal field theory, today's class we are going to discuss regarding the tetrahedral distortion of octahedral geometry. We are going to discuss the tetrahedral distortion of octahedral geometry. The shape of the transition metal complexes are affected by whether the d orbitals are symmetrically or asymmetrically filled. The shape of the transition metal complexes are affected by whether the d orbitals are asymmetrically or symmetrically filled. Repulsions by the 6 ligands in an octahedral complex splits the d orbitals on the central metal ion into T2G and Ag levels. Therefore, there is a corresponding repulsion between the d electrons and the ligands. The repulsions by 6 ligands in an octahedral complex splits the d orbitals on the central metal into T2G and Ag levels. There is a corresponding repulsion between the d electrons and the ligands. Now, if the d electrons are symmetrically arranged, they will repel all the 6 ligands equally. Thus, the structure will be a regular tetrahedron. If the d electrons are symmetrically arranged, they will repel all the 6 ligands equally. Thus, the structure will be a completely regular tetrahedron. If the d electrons are asymmetrically arranged, they will repel some ligands in the complex more than the other. If the d electrons are asymmetrically arranged, they will repel some ligands in the complex more than the others. The structure is distorted because some ligands are prevented from approaching the metal as closely as other. Here, if the d electrons are asymmetrically arranged, the distortion occurs because some ligands are prevented from approaching the metal as closely as other. The Eg orbitals point directly at the ligands. Asymmetrically filling of the Eg orbitals results in some ligands being repelled more than the others. Here, the Eg orbitals, if they are asymmetrically filled, what happens is some ligands are being repelled more than the others. This causes significant distortion in the octahedral shape. So, what do we observe is the distortion mainly occurs when the ligands are going to be repelled to a different extent while they are approaching the central metal atom, and this mainly reason is mainly due to the asymmetric arrangement of the electrons in the d orbitals. The Eg orbitals point directly at the ligands. Asymmetric filling of the Eg orbitals results in some ligands being repelled more than the other. The Eg orbitals point directly at the ligands. Asymmetric filling of the Eg orbitals results in some ligands being repelled more than the others. This causes a significant distortion in octahedral geometry. In contrast, the two Tg orbitals do not point directly at the ligands. In the T2 or 2G orbitals do not point directly at the ligands because here they are dxy, dyz and dxz, but point in between the ligand direction. Asymmetric filling of the T2G orbitals. Has very small effect on the stereochemistry. Distortion caused by asymmetric filling of T2G orbital is usually too small to measure. The two Eg orbitals which are degenerate, dx square minus y square and dz square are degenerate. If these two degenerate orbitals are asymmetrically filled, then the degeneracy is distorted. If these two orbitals are asymmetrically filled, then the degeneracy is distorted. The two orbitals are no longer going to have equal energy. If the dz square orbitals contain one more electron than the dx square minus y square orbital, then the ligand approaching along the z and z axis, that is from plus z and minus z, will encounter greater repulsion than the four ligands. If we observe there is one more electron, if in the dz square, if there is one more electron in the dz square than dx square minus y square, then the ligand approaching along the plus z and minus z will encounter greater repulsion than the four ligand. The repulsion and the distortion results in the elongation of the octahedron along the x-axis. This elongation is called as tetrahedral distortion. Strictly, it should be called as tetrahedral elongation. If the dx square minus y square orbitals contain extra electron, then the elongation will occur along the x square minus y square. If dz square contains one extra electron, then the elongation was along the z-axis. But if dx square minus y square contains an extra electron, then the elongation will occur along the xy axis. This means the ligands approach more closely along the z-axis. Thus, the four ligands, four long bonds and two short bonds. The ligands approach more closely along the z-axis. Thus, there will be four long bonds and two short bonds. This equivalent to compressing of the octahedron along the z-axis, and this is called as tetrahedral compression. Now, let us see example of a crystal structure of chromium hexafluoride. This has a distorted rutile titanium oxide structure. Now, chromium 2 plus is octahedrally surrounded by 6 ligands. Chromium is surrounded by 6 ligands, and there are 4 chromium fluoride bonds with length 1.98 to 2.01 angstrom and 2 longer bonds with 2.43. The octahedron is said to be tetrahedrally distorted. If we are going to see the electronic arrangement of chromium 2 plus, it is D4. It is going to have D4. There is F minus is a weak field ligand. So the T2G levels contain 3 electrons and the EG level contain 1 electron. The dx square minus y square orbitals has 4 lobes, while the dz square has only 2 lobes, pointing at the ligands. To minimize the repulsions of the ligands. Now, to minimize the repulsion with the ligands, the EG electron, because EG has got an extra electron, the EG electron will occupy the dz square. This is equivalent to splitting the degeneracy of the EG level so that the dz square is of lower energy. That is, it is more stable, and dx square minus y square is going to be of higher energy and it is less stable. Thus, the two ligands approaching along the plus z and minus z are subjected to greater repulsion than the 4 ligands approaching from plus x minus x plus y minus y. This causes the tetrahedral distortion. This causes the tetrahedral distortion with 4 short bonds and 2 long bonds. So this is regarding the tetrahedral distortion in an octahedral complex. Now let us see another example of copper. Copper 2 salts and complexes also show tetrahedral distortion. Copper with electronic configuration D9 and Cu2 plus, it has got totally 8 electrons in the d orbitals. Cu2 plus, it has got D9 configuration and there are in 2 plus state there are 8 electrons in the d orbitals. That is T2G is going to be having 6 electrons and EG is going to be unsymmetrically filled with 2 electrons in one orbital and 1 electron in the another orbital. So this electron can be present in, whether it is going to be present in dx square minus y square or dz square. To minimize, so here we are going to see here the T2G. Here we are going to have the electrons. So now what happens is, in this case, if the electrons are going to be present here, what happens? There is going to be a splitting. Now to minimize the repulsion, the ligands with 2 electrons occupy the dz square and the electron occupies dx square minus y square orbital. Thus the 2 ligands along the z plus z and minus z are repelled more strongly than the 4 ligands. Therefore, when dz square and x square minus y square orbitals are unequally occupied, the distortion occurs, and this is known as Jahn-Teller distortion. And Jahn-Teller theorem states that any nonlinear molecular system in a degenerate electronic state will be unstable and will undergo some sort of distortion to lower its symmetry, and this is mainly because it is going to lower its symmetry and remove the degeneracy. Okay students, thank you.